Hi, today our group will present about MEMS passive wireless system for capacitive gas sensor. Our group members are Ong Wee Chet, Wang Chi-Yu, and I, Liang Fei. So this is the content of our presentation. First is its introduction, then simulation components, then the interdigitated electrode structure, then simulation result, and then finally conclusion. So now I will talk about the introduction. As we all know, in the recent year, the use of SAW resonators in the sensor system are very common because of the growth of the wireless communication. The advantages of using the SAW resonator is that the resonator itself can be kept protected from the disturbing environmental influences. From figure 1, it shows the principal circuitry of the sensor. As you can see, there are two resonators and the matching networks, which include two inductors, and there's a sensing capacitor. The two SAW resonators can reduce the disturbing influences due to the radio channels to the system, and then the changes on the matching network will cause a shift of the resonance frequency over a certain range. In the system, the output is the change in difference frequency of the two resonators. So for better protection against disturbing influences, a double resonator circuit is chosen and the matching network should be as minimal as possible. Figure 2 shows the frequency response of the sensor. The frequency response of the sensor is a double peak at the two resonance frequency of the SAW resonators. The two resonators with different Q factors and different impedance behave differently. The equation S1 times F1 plus S2 times F2 equal to delta F shows that the change of the difference frequency depends on the sensitivity S of each resonators. So this is the simulations components of our design. There are two resonators. One is RO3101, another one is RO3112. This value can be get from the datasheets of the resonators. The second component is the inductors, which is a part of the matching circuit. And the last one is the sensing element, which is a capacitor to sense the gas. So next I will pass to the next group member.
Okay, I'm Ong Wee Chet, and I'm now going to present about the interdigitated electrode structure, also known as IDEs, used in our capacitive gas sensor. Okay, this structure is used to design a simple planar capacitive sensor that can be integrated with other electronics. It can achieve high capacitance in the smallest scale possible. This is due to the structure of this interdigitated electrodes, which it has a few figures and beams with the width of W, and they are separated by a space of S. Okay. This structure can be modeled as a parallel capacitors, which it causes the capacitance to be higher than other structure. Okay. The overall structure, the overall capacitance of this structure is the sum of the sidewall capacitance between the beams of fingers, and also the fringe capacitance that appears on the edges, which is around the fingers here. Okay. So in this structure, the IDEs will be covered with a gas-sensitive material that has varying permittivity on gas absorption, which means that when it is exposed to different gases, the permittivity will change according to the gas absorption, the gas, and the capacitance will change accordingly. Okay. now we have the 3D cross-section of the unit cell. This is actually the cross-section of the electrode, the interdigitated structure just now. Okay. In this structure, the gas sensitive film will grown to fill the spacing between the IDEs, which is here. Okay. And the spatial wavelength of the IDE is defined as a lambda, which is equal to 2 times the width and the spacing. Okay. And the change in capacitance is linearly proportional to the relative permittivity of the sensing film. Okay. This linear relation does not depend on geometry of the IDEs. Okay. So any change in the relative permittivity due to the gas sensed by this sensor will cause the capacitance to change. Okay. And this relation does not depend on the geometry of the IDEs, which is the width and the spacing here. Okay. Okay, so now I will explain about a few factors that can affect the sensitivity of this gas sensor. Okay. At the same permittivity, the larger the spacing between the fingers, the greater the change of capacitance, which means that the sensitivity of this gas sensor will be higher. Okay. And in area-wise, the area of the IDEs actually has no effect on the sensitivity. This is because the changes in C and the capacitance is actually the same. I mean, the ratio of the change in capacitance and the capacitance itself is actually the same. That's why there is no effect in the sensitivity. Okay? But when the area increases, the capacitance decreases, and it causes the sensor to become less susceptible to the noise. Okay. Next, the sensitivity increases when the sensing film thickness increases. Okay. This is because more film lines pass through the sensitive region, and until the saturation occurs as the thickness reaches half the wavelength of the IDEs. Okay. Where TF equal to lambda over 2 equals to W plus S. Okay. Finally, the thickness of the metal can also affect the sensitivity of the sensor. As the thickness of the metal is increased, the electrodes the surface of the electrodes will be increased, and therefore there is an increase in the sidewall field capacitance, and so the sensitivity increases. Okay, that's all from me. Thank you.
Now I will present about the simulation result for the design capacitive gas sensor system. This simulation is done with the AWR software from the National Instrument Company. The gas sensor capacitance is varied from 6 picofarad to 14 picofarad. Figure 6 shows the complete circuit of this system. By using this software, the two inductors in the matching circuit are tuned manually in order to obtain two very sharp peaks in the frequency response of the system. When the simulation is performing, if the frequency response can be obtained as shown in figure 7, in which two very sharp peaks can be obtained from this curve, in which the peak is located at the 433.359 MHz and 433.908 MHz. If the value of the gas sensor capacitance varies, the location of the two peaks will change correspondingly. Figure X shows the graph of the difference frequency versus the gas sensor capacitance variation. Since the characteristics of these two resonators are different, So the variation of F1 and F2 with the change in the gas sensor capacitance are not the same. The difference frequency in this curve is not constant at all times except when the gas sensor capacitance is varied from 9 picofarad to 11 picofarad. The difference frequency is constant. The slope of this curve is defined as the sensitivity of the sensor. So from this curve, the average value of the sensitivity is 1 kHz per picofarad and its percentage relative sensitivity is 0.182% per picofarad. In conclusion, the design gas sensor capacitor system consists of two single port resonator, two inductor for impedance matching, and a gas sensor capacitor as a sensing element. The mesh inductance for the RO3101 is tuned at 10.49 nanohenry, while the mesh inductance for the RO3112 is tuned at 16.02 nanohenry in order to obtain two very sharp peaks at the frequency response of the system. The difference frequency of these two peaks is constant only when the gas sensor capacitance is varied from 9 picofarad to 11 picofarad. Otherwise, the difference frequency varies proportionally to the variation of the gas sensor capacitance. That's all of our presentation. Thank you.